Hi again, everybody, and welcome back. This is our continuation of our Chapter 4 notes on 2D kinematics and projectile motion. And we had just gotten done doing problems with a zero launch angle. Now we're going to be looking more specifically at problems with what you might call a general launch angle, or any launch angle other than 0 degrees, anything other than perfectly horizontal. So we have a specialized equation right here called the trajectory equation, which we can use. Now, I have written down here that it's usually less useful than other equations, and there's some truth to that, and that is because it's the more specific you get with equations, that is, the more of a niche equation you get for a certain scenario, the less helpful it is in other scenarios. All right, but this is based on our knowledge that in the x direction there's no acceleration, which is why this part in the y direction right here that has the acceleration of gravity, that's why it's cut off here in the x direction. So we can say the displacement in the x direction is going to be initial velocity in the x direction times time. We can say that that motion is going to be completely independent of the motion in the y direction, with the exception of one linkage or one value that is the same between them. And of course, we're talking about time. All right. So what the trajectory equation does is it puts those statements for displacement in the x and displacement into the y into one equation and actually substitutes out time. This is what I mean. So in the x direction, and I'm going to kind of highlight this in green, we know that the displacement in the x is initial velocity in the x direction times time. All right, and so of course the x component of initial velocity is vi times a cosine of theta, which is what that is right there. So we're going to simply just turn this around and solve for t. So we have, with regard to the x direction, t equals the x displacement divided by vi cosine theta. All right, that's written in terms of t for a very specific reason, because we can also talk about the y direction in terms of t. We've got y here, delta y, is a function of initial velocity in the y direction times time, okay, plus 1/2 at squared or minus 1/2 gt squared, however you want to do it. But we've got time here and here as well. So if we take that statement for time right here that we kind of established in with regard to the x direction, we can plug that in there and there for our time in the y, because the assumption, and it's certainly true, is that the time spent in moving in the x is the exact same thing as the time spent moving in the y direction. So if we do that, if we plug all those in, we get this equation at the bottom. Actually, we don't. There's a typo in here that I'm going to ask you to add to. So you stick t, so this value for t in here and square it, and this value for t in here and square it. You get something that should have a delta x squared in the numerator, and I left that out originally. Okay. So that means that the time has been substituted out. All right, we've substituted things in for time, so the time goes away. And we have really our y displacement, that's our delta y right here, kind of as a function of our x displacement, which is right here, and I should rewrite that, and as we wrote in, up top in the numerator over here as well. Okay? The assumption is that you know the initial velocity right here, and that you know the angle theta, and of course g, or the acceleration of gravity, is constant. So this is really saying, let's say you have an initial velocity right here. Initial velocity equals, I don't know, 12 meters per second, and it's at some angle theta. Theta equals 35 degrees above the horizontal. That says for any value x, so if you know the initial velocity and direction, for any value delta x, the answer that will return you the corresponding displacement in the y direction. So that means your ball, or let's pretend it's a football, all right? So your football is going to be right there if it started there. So it tells you your y displacement in terms of your x displacement. So over time, this thing has kind of gone up and has taken that path like that. All right, so it drops out time. And it is kind of specific, so it's not super helpful, but it can help you out of a jam, especially if you don't know time, because the assumption is time is equal in the x and y directions. So we're going to We're going to apply that to a problem and solve it, and then I'll give you 2 more equations, and then we'll be done with this scenario. Okay, so we have something that pertains to our Downingtown East kicker. In the big game, 1 second left and down by 2 points, the Downingtown East kicker needs to make a 36-yard field goal. All right, now in the football, we measure things in yards, but we don't do that in our physics. So that's going to just become 32.19 meters. So that's the actual distance. All right, in fact, let's just go ahead and draw it. All right, so here's our field right there. Suppose it to be perfectly flat. All right, so there's our kicker kicking the ball. Yes, I know it's a very, very poorly drawn kicker. Here's the football right there, and it has to make it over. I'll make orange field goal post. How's that? And it has that kind of curvy thing like that. All right, and it has to go up and through the goalposts in order to win the game. All right, a couple other things that we're told is that the displacement, the x displacement from there to the goalposts, is 32.19 meters. All right, and how high are the goalposts? Well, they're a standard 10 feet, but we're not going to measure that in feet. We're going to measure that in meters. So our delta y equals 3.05 meters. All right. So the question is really, will he make the kick if he kicks the ball with an initial speed of, all right, so let's write this in. 19.65 meters per second. So initial velocity equals 19.65 meters per second. And the angle the kicker always kicks at, for whatever reason, is going to be 50. I should just write a theta in there. Theta equals 50 degrees. Theta equals 50 degrees above the horizontal. I asked a kicker if they always kick at the same angle, and the answer was no. It depends on how far away you are from the goalpost. But let's just pretend this kicker is super precise and always kicks at the same angle at 50 degrees, okay? Will he make it? Well, what question A is asking is really, assuming he makes it to the goalpost, which is 32.19 meters away, is delta y going to be greater? Let me just start that again. Is delta y greater than 3.05 meters? 3.05 meters. Big question mark, okay? So we're assuming he's going to make it to the goalpost, but will it be higher or lower? Now, I realize that with football kickers, usually the problem is, are they too far left or right? They usually miss it left or right. They don't miss by falling short normally. But we're going to pretend this guy has perfect aim. He just has issues with getting it to the goal post to the right distance. So that's what we're going to focus on. All right. So let's write down our equation. What is our equation? Our equation is going to be, and I'll write it in red down at the bottom. Oh, and by the way, I want to clarify something here. The delta y, and hey, look at that. Thankfully, it's already in the form that we want to solve for, right? Delta y equals delta x, the x displacement times the tangent of theta, right, minus the quantity delta x squared times g, acceleration of gravity, divided by 2 initial velocity squared times the cosine squared of theta. Cosine squared of theta, what does that mean? Well, that's really like saying cosine of theta squared. That's really saying that right there. All right. The problem is if you don't write in the parentheses, and so if you just do that, then it looks like you're squaring. It looks like a question mark now. It looks like you're squaring a theta. You're not squaring a theta. You're squaring the cosine of theta. All right. So if it helps, in fact, when I write it in, I'm going to write it as cosine of theta, the quantity squared. That's what that means, but that's why we put the squared in front or after the cosine instead of after the theta, because we're not squaring the theta. All right, let's just key in our values, and we'll write in our values, and then we're going to key it in on our calculator. So our x displacement is 32.19 times the tangent of what? That's 50 degrees, right? Minus the quantity, 32.19 the squared times 9.81. And I'll put brackets there too, all right? divided by 2 times the initial velocity, which is 19.65 squared, right? 19.65 squared times the cosine of 50 squared. Cosine of 50 squared. So we're squaring the whole cosine of that. Okay? So this will tell us what the height, or you might say the y displacement of the ball will be when it gets to the goalposts. All right, and if you do your math, crunch your numbers, we're going to get a value of 6.51 meters. All right? So when it gets to the goalpost, it'll be at a y value, or y displacement of 6.51 meters. So look at that. Hooray, it works. All right? It's greater than the required height to get over the crossbar. It's greater than 3.05. So he splits the uprights, gets over the crossbar, and we win the game. Okay? Excellent. Really, more than anything, that was just kind of plugging in. More than anything, that was kind of a calculator problem because there's a lot of things going on down here. You really want to make sure you have your parentheses in the right area and you do your order of operations correctly. Now, part B of this says, okay, well, if he wants to just barely make it to the crossbar, what must the minimum speed be? Okay, so I'm going to go to the next slide right here. Or am I? Yeah, I'll make another slide. I got a blank one right here. All right, so again, I'm going to draw our kicker. There's a field, and he's kicking the ball. I do that stick person very, very backwards. But there's a couple, like some different parameters right here. Okay. First of all, well, let's just finish drawing the ball in there. Okay. There's a ball. The initial velocity is an unknown because let's say he can't kick it with that value of 19.65. Initial velocity is our unknown. So that's what we're solving for right there. VI, or I should say VI min, right? The minimum initial velocity. You can always kick it harder than that and get it far over the goalpost. But the very minimum to get it right to the goal crossbar, what is that going to be? All right, well, some other things that are true. And by the way, this is part B. All right, some other things that are true is that the x displacement is the same. All right, delta x equals 32.19 meters, and it's also true that the height that he has to make it to, delta y right here, equals 3.05 meters from there to there. Okay, those things have to be true. So it's really just going to be a matter of rearranging our equation to solve for the initial velocity. All right, so we have an equation that looks like this. Delta y equals displacement in the x direction times the tangent of theta. And I'm using all general terms right now, minus delta x squared times g, all over 2 times the initial velocity squared. So that's what we're solving for right there, times the cosine squared of theta. I wrote it as cosine of theta, the value squared, even though cosine with the square after the cosine is the more correct way to write it. All right, well, we're solving for our v initial right there. So we got some problems. It's in the denominator, it's squared, and it's being subtracted right here. So the first thing I'm going to do is take this whole fraction right here and add it to the other side. All right, so it becomes positive. And then I'm going to subtract the delta y away from it so it comes over here. So it's going to look like this. Delta x squared times g over 2 times initial velocity squared times the cosine of theta squared equals delta x times the tangent of theta minus, oops, I forgot the minus, minus delta y. Okay? Now we're still solving for the initial velocity right here. So we have it down here in the denominator and it's squared. What we're going to do is we're going to multiply by vi squared on both sides. So it'll cancel out on this side and it will appear in the numerator over here. Now the problem is it'll be next to all this mess right there. So why don't we take this, put some brackets around it and say, all right, well, let's just divide by all that and bring it down here. So essentially, the vi squared and everything in the brackets right there are going to just change position. Okay? So it's going to be VI squared is going to equal, and well, you know what, I'm going to write it the way that I have it written here. Delta x squared times g over, and I'm making a long dividing line right there, 2 times the cosine of theta, the value squared, times delta x times the tangent of theta minus delta y. Okay, all that equals, I'm going to shorten this a little bit, equals VI squared. Now, we could write it all over again and take the square of the VI out, but why don't we just say, okay, we know that we need to square root both sides, so I'm going to just erase that and then just put a big old square root. Not a very well drawn one, is it? Big old square root right across the top like that. All right? That could be possibly the biggest denominator in a square root you've ever done. So we're going to have the square root of, can I even fit it all in there? Well, we'll see. I don't think I will be able to. I'm going to write down at the bottom. VI is going to equal, and I should say VI min, right? The minimum initial velocity required to get it to the goalpost, because that the very minimum it's got to cross at 3.05 meters, is going to be 32.19 squared times 9.81. Okay? Divided by 2 times the cosine of 50 squared times 32.19 times the tangent of 50 minus delta, delta y. What is delta y? It's 3.05 minus 3.05. Now what I'm going to do is I'm going to put this, and I'll draw it in black so you can see it. Remember, this whole thing is one expression right there, so it's all this times this whole quantity. So don't multiply these and then subtract 3.05. You want to multiply this whole second part by 3.05. All right, so key that in. What do you get? According to my calculations, I get somewhere in the neighborhood of 18.7. 18.7 meters per second. That's the minimum initial velocity required just to barely get it to the goalpost, and maybe it hits it and bounces over or something like that. All right, but it's definitely less than the original velocity. So isn't that interesting? So you've got 18.7 is the very minimum. If we go back one slide, the original velocity, 19.65, isn't enough to get it 3 meters over the crossbar. But if you drop that velocity by just 1 meter per second, it's going to drop the height of it at the crossbar a whole 3 meters so that it just barely clunks over and wins the game. All right, so that's good news. In both cases, they win the game, but we have to know what that minimum initial velocity is for the kicker in Part B. All right, well, for right there, I think I'm going to stop. The next section will be on the range equation and on the max height equation. But this was our real application that we were going to do for today. So thank you in the meantime for following along, and make sure you ask me any questions, and I'll see you on the next one.